We've all heard the pitch for pyrolysis, right? This sort of magic box that can take our mountains of trash and turn them into valuable oil. I mean, it sounds like the absolute perfect solution for our waste and energy problems. But how much of that is actually reality? Well, today, we're going to find out what really needs to go into a pyrolysis reactor to make the whole thing work.
It really all comes down to this one simple, totally inescapable rule. And this isn't just some catchy phrase, It is the fundamental law of chemical recycling. The quality of what you put in directly dictates the quality of what you get out, period.
Okay, so let's get this straight, right from the very beginning. On the one hand, you've got the myth, this magic box that turns any old garbage into black gold. But on the other hand, you have the reality, a sensitive, precise chemical process. It is not magic, not by a long shot, and it proves the core lesson for today. For pyrolysis, the feedstock, well, the feedstock is everything.
So let's dive into that reality check. Probably the biggest misconception out there is that the raw material, the feedstock, for these plants is just free for the taking. The truth, quality costs money, a lot of it.
Just look at this price tag. This isn't for some fancy specialty chemical. No, this is the real-world market price in Europe for clean, sorted bales of polyolefins. The exact kind of plastic you need for this process to work well. So the key insight here is that the pyrolysis business model isn't built on free trash. It's about paying for a very specific, clean raw material.
All right, now let's talk about a different type of feedstock, biomass. Things like wood chips and straw. Now, this is actually the oldest form of pyrolysis, but it comes with a huge built-in chemical challenge that we call the oxygen problem.
See, unlike a simple plastic, biomass is a really complex composite of these big three. You've got cellulose, hemicellulose, and lignin. And the key takeaway here is that all of these molecules are just loaded with oxygen atoms, which really complicates the chemistry and ultimately leads to a lower quality oil.
But you know what? The oxygen that's trapped inside the molecules isn't even the biggest issue. This number is up to half. That's right, 50% of the weight of fresh, green biomass can be nothing but plain old water. And that brings us to something called the moisture penalty. I mean, think about it. Before you can even start breaking down the wood, you have to boil off all that water. This just consumes a massive amount of energy, completely killing your efficiency. And what's worse, it can create this watery, low-energy sludge instead of the valuable oil you were hoping for.
So what about plastic waste then? Well, the exact same rule applies. You can't just throw everything in there. There are gold standard plastics, and then there are the contaminants, the ones that can bring an entire operation to a grinding, catastrophic halt.
Okay, this is the gold. The ideal feedstocks are the polyolefins, polyethylene and polypropylene. So why are they so good? Well, it's because they are pure hydrocarbons, just long chains of nothing but carbon and hydrogen atoms. When you break those down, you get other, smaller hydrocarbons, which is exactly what you want for making high-quality fuel or even new plastics.
So the crucial point is this. If it's not carbon or hydrogen, it's a potential problem. Any other atom, oxygen, nitrogen, or chlorine can cause absolute havoc in the system. And there's one plastic in particular that is the undisputed king of contamination.
Meet public enemy number one for any pyrolysis plants, PVC. We see it everywhere, in pipes, flooring, packaging. But its chemical makeup, that C for chloride, makes it an absolute nightmare for this process.
So here's what happens. The second you heat up PVC, it releases its chlorine atoms. And those atoms immediately grab onto hydrogen and form hydrochloric acid. Yeah, you heard that right. You end up creating a highly corrosive acid vapor inside your multi-million-dollar reactor.
And the result? It's utterly devastating. This isn't some long-term wear and tear issue. As the source material bluntly states, this acid can literally eat through a standard carbon steel reactor in a matter of days. The damage is swift and it is catastrophic.
And PVC isn't the only troublemaker in the bunch. PET, the plastic used in drink bottles, it forms these solid crystals that can completely block up pipes downstream. And then you've got plastics like nylon or polyurethane, which contain nitrogen, and that can poison the really expensive catalysts that are used to upgrade the oil.
All right, so the next common feedstock seems like a perfect solution. End-of-life tires. I mean, there are billions of them, and they're packed with hydrocarbons. But just like everything else we've seen today, a tire is far more complex than it looks.
Now, you might be surprised to learn that less than half of a modern tire is actually rubber. The rest is this complex composite. You've got carbon black for strength, steel wire for structure, and a whole cocktail of additives, including one particularly problematic element, sulfur.
That sulfur? which is used to make the rubber durable in a process called vulcanization, it doesn't just disappear during pyrolysis. Nope, it gets distributed across all three outputs, the solid char, the liquid oil, and the gas. And its presence in the oil is a major economic headache.
This comparison here shows the problem crystal clear. Oil from tires has about 1.5% sulfur, but most fuel regulations demand less than 0.5%. That huge gap means the oil can't be sold as is. It needs expensive, additional processing just to remove that excess sulfur.
So with all these contaminants floating around, water, PVC, PET, sulfur, how does a real plant actually operate without self-destructing? Well, the answer is you have to build a robust, multi-stage defense system before the feedstock ever gets near the reactor. This is the feedstock firewall.
And this isn't just some simple filter. It's an entire industrial process. First, you shred everything down. Then, powerful magnets pull out any steel. Next, and this is the really high-tech part, near-infrared optical sorters scan all the material, identify problem plastics like PVC and PET in milliseconds, and then blast them out of the stream with these little precise jets of air. Finally, you densify the light, fluffy plastics so they can be fed into the reactor smoothly.
And this brings us to the most important point of all. Pre-treatment isn't an optional extra you can just skimp on to save a few bucks. It is the absolute, non-negotiable firewall that stands between a smoothly running, profitable plant and a corroded, clogged-up disaster.
So what we've seen is that the success of pyrolysis is overwhelmingly determined before the process even really begins. It is all about rigorously controlling the input. Which of course leaves us with a final critical question. If getting the feedstock right is this complex, what on earth does it then take to refine and perfect the oil that comes out the other end?